Dear learners, welcome you all in today's session. The topic of the session is binary search tree. We will discuss in fact the creation of binary search tree, insertion as well as deletion. I hope all of you are aware with the binary tree. So in binary tree we already know that every node may have maximum 2 children. So 0 to 2 children. Non-leaf nodes may have either 1 or 2 children, whereas leaf nodes have 0 children. So there is no other constant on binary tree, but we will discuss binary search tree where are certain constants on it. It is also a kind of binary tree but with certain constant. We will discuss what are those constants and then we will discuss the various operations. So after going through this session, in fact the learners will be able to learn the fundamentals or the introduction of binary search tree, which is in short known as BST. They will also learn how to create BST for a given set of keys or inputs, and they will also learn how to perform different operations on the BST. So these will be these are the objective or outcomes of this session. So what is BST first? So BST in fact is a non-empty BST satisfies certain conditions. So I am talking about non-empty BST which have certain number of keys. So it should satisfy certain properties, then only it is BST. Otherwise it is not a binary search tree. The first condition is that the key, if we consider any key, whether it is a root or any non-root key, then the key in the left child of a node, if it exists, if left child exists, then it should be less than the key in its parent node. That is the first condition. So if there is a key to its left child, there will always be lesser key or less keys or smaller keys, whereas the keys in the right child of a node, if exist, is greater than the key in its parent. So these are two basic conditions. Left child will be always smaller and right child will be greater, and this the left and right subtree of the root are again binary search tree. So it means this property, the previous two properties, are applicable for every node of the binary tree. Then this is known as binary search tree. Sometimes we have equal number of keys also. So in that case the equal key will go to the right side of a particular key. So greater or equal keys will go to the right child, go as a right child, and smaller will be to the left child. And one of the basic advantage we can say, or the basic property of binary search tree is that if we do its in order traversal, then it always gives the keys in sorted order, that is in ascending order. So we already know that there are certain types of traversal methods, like in order is one of them, pre-order is another, post order is another, but here I am talking about the in order traversal. So in order traversal of BST will always give the values or keys of the tree in ascending order, that is in sorted form. So now the question is, if we have been given set of inputs, set of keys, so how we can create a binary search tree? Like in binary tree there is no constant, anywhere we can add the keys, whether we can ask from the user whether we want to add it into the left child or into the right child as a right child of a node, we can do that. But in this case we cannot do like that. Here we have to follow the properties of the BST. So I will explain the creation of binary tree with the help of one example. Let we have been given the keys like 10, 25, 25, 30, 24, 12 and 2, and we want to create BST when these keys are inserted in the order. That is, first 20 is inserted, then 10 is inserted, then 20, then 5 and so on. So initially the BST is empty. So first we will consider the first key, that is 10. So a binary search tree is constructed basically by the repeated insertion of new nodes into the binary tree structure. So initially it is empty, then we have to insert the first key, that is 10. So because it is the first element, so we can insert it like this. So here we can see that out of this stage, because there is no other keys, so 10 is the only key, so our BST will contain only 10. Now the next key to be inserted is 20. So we know that we start from the root and compare this new key to be inserted. So we know that 20 is greater than 10, so it will be the right child of 10. So 20 will be inserted as a right child of 10 and we will get this BST after inserting 20. Now next is 5, key 5. So we have to again compare this 5 with the root, that is 10, and we know that 5 is less than 10, and as per BST the left keys lesser keys or smaller keys should be into the left subtree of the BST, existing BST. So 5 is compared with the 10 because it is smaller than 10, so it will be the left child of 10, and after this insertion the BST will be like this. Then next key to be inserted is 25. So again we will compare this 25 with 10. Because it is greater, then we will go to the right and will compare it with the 20 because it is also greater than 20. So the 25 will be inserted as the right child of 20, and the key the BST at this stage will be as shown here. Now next insertion will be 30. So 30 again we will compare with 10. Then it is greater, go to the right. It is 20, compare with that, go to the right. It is 25, still 30 is greater than 25. So it will be the right child, it will be inserted as the right child of 25 and the BST will become like this. So after 30 we have 24. So 24 again we will start comparing it with the root, and we know that it is greater than root, that is 10. Then it will be compared with 20, still it is greater, and then it will be compared to the right child of 20, that is 25. Here 24 is smaller than 25, so it will be inserted as a left child of 25, and after inserting this 24 the BST or binary search tree will look like as it is shown here in this slide. So next key to be inserted is 12. The same procedure we will follow. Compare with the root, it is bigger than the root, that is 10. Then go to the right, compare with the 20, but it is smaller than 20, so it will be inserted as the left child of 20. So BST will look like this. And finally we have the last element, that is 2. So it will be compared with 10, it is smaller. We will go to the left side and we will compare it with the 5. Again it is smaller, so we will insert it as a left child of 5. So for the given keys which I have shown here, the final BST will look like this. So we can see here that the properties of BST are satisfied. That is, for any node, all the nodes which are to its left subtree are smaller and the nodes which are in the right subtree of it are greater. For example, if we see the 20, if we take say the root node 10, so we can see that to its left subtree we have all smaller keys, that is 2 and 5, and to its right subtree we have all bigger keys 20, 12, 25, 24 and 30, and this is true for every node. For example, if we see the 20, key number 20 which is right child of 10, so to its left subtree we have keys 20 having the value 12, but to its right subtree we have all bigger values. So that is how we can create a BST for the given set of elements. So I hope it is clear to all of you. Now, what are, apart from the creation of BST, what other operations are there which can be performed on binary search tree? So few of the operations are being mentioned here, like creation of a tree BST from empty, so that we have already seen. Then the next operation which we can perform is traversing the BST. So as we know that there are three types of traversal methods: in order, pre-order and post-order. We will see its example in next slide. So this is another operation which we can perform. Similarly, we can insert a new node into the existing BST. So that example we already have seen. We can search for an element. This is one of the application we can say of BST, that we can search any given element in lesser time in comparison to linear search, where we have to search each and every element to find a given key. Here in this BST we have to search it fastly, like we compare the root, the keys to be searched from the root, and we may know whether it is smaller than root or greater than root. If it is smaller, then we have to search it into only left subtree. We don't have to go into the right subtree. So we can ignore the right subtree. Similarly, we in the same process can be followed in the entire left subtree, and that way we can find finally whether there is the node to be searched is existing or not. So if the BST is almost balanced by binary search tree, then in that case the order of time complexity to search an element will be of order log n, because every time we are ignoring approximately half of the elements in one step. So if we calculate the time complexity, it will come out to be order of log n. Similarly, we can find the smallest element. So obviously, because it is BST, so we know that the smallest element will be there. If left subtree exists, then the smallest element will be existing into the left subtree. So from the root we will go to the left child, then further we will go to the left of the left child if it exists, and so on. So we will get the smallest element. In the similar way, we can find the maximum or largest element, or we can perform the deletion operation. This is another important operation. So we will discuss this operation in next slides, in fact. So before we discuss the deletion operation, let me discuss the traversing the BST. So as I told you that traversal of BST can be performed in three methods, that is known as in-order traversal, pre-order traversal and post-order traversal. What we do in in-order traversal, we first start from the root, we go to we traverse the left subtree, and then we traverse the node, and then we traverse the right subtree. For example, in this case, if we want to perform the in order traversal, so we will start from the 10 and then we will go to the, because there is left subtree, we will go to the left, then we will reach to the 5, and after this we have further left nodes existing, that is 2. So we will print this 2 first and then we will go one level up because there is no further nodes existing either to the left or right of the key 2. Then we will go one step further and will print 5. So first 2, then 5, then we will go, because there is no left subtree existing to the key 5. So we will go one step up, one level up, and we will print 10. So 2, 5, 10, and then all the left subtree of 10 are reversed. So we will go to the right subtree, we will reach to the 20, and then we will go to the left of 20. So we have only single element existing to the left subtree of 20, that is 12. So 12 will be printed next, and then we will go one level up because there is no further nodes in the left subtree. So 20 will be printed, and then we will go to the right subtree of 20 and 24 will be printed, 25 will be printed, and 30. So in order, the sequence of traversing the nodes for this BST will be first 2, then 5, then 10, then followed by 12, 20, 24, 25 and 30. So this is in order traversal. In the beginning I told that if we do the in order traversal of binary search tree, then we get the keys in ascending order. Here we can see that we are getting the keys in the ascending order, that is in sorted order from smallest to largest. Similarly, when we perform the pre-order traversal, so first we traverse the root, then we go to the left subtree, and then we go to the right subtree. That is the algorithm for pre-traversal. So we will start from root, that is 10. So 10 will be printed first, then we will go to the left subtree, 5 will be printed, then 2 will be printed. So we have completed the left subtree of root, that is 10. Then we will go to the right subtree, and first node to be encountered is 20. So 20 will be printed, then 12, and then same way 25, then followed by 24 and 30. So this is how we can do the pre-order traversing of a BST. The third method is post-order traversal, in which we first traverse the left subtree, then we traverse the right subtree of a node, then finally the root. So here in this case we start from the root and go to the left. So 10 will not be printed till all the nodes to its left subtree and right subtree are traversed. Similarly, when we reach to the 5, the left child of 10, this 5 will not be printed or accessed till all the nodes to its left subtree and right subtree of 5 are traversed. So we will go to the 2. So there is no left subtree or left node or right node to the 2. So we will first print 2. Then we will come one level up and we will print 5, because 5 do not have any right subtree. So after printing 2, then 5, we will reach to the 10. But 10 will not be printed because it have right subtree. So until unless entire right subtree nodes are not printed, we cannot print 10. So we will go to the right child, that is 20. Again in the same way we will go to the left. We will print 12, and the 20 will not be printed till all nodes in the right subtree are printed. So we will reach to the 25, then 24 will be printed. So then right child of 25, 30 will be printed. Then now all the nodes in the left as well as in the right of 25 are printed. So now we can print 25. So then 20 and finally 10. So the sequence of traversal in post order will be first 2, then 5, then 12, then 24, 30, followed by 25, 20 and 10. So pre-order traversal, in the post-order traversal, we will get the keys traversed in this order. So this is how we can perform the traversing of a binary search tree. So here we can see that the in-order traversal of this is very useful because we get the elements in sorted order. Now I come to the another important operation which we can perform on binary search tree, and that is deletion of a node. So to delete a node with given key from a binary search tree is not basically a simple process. There may be number of cases, basically 3 cases. We will see all those 3 cases one by one. 3 cases arise. The first case is that if the node to be deleted has no sons, neither left child nor right child, then it may be deleted without further adjustment to the tree. So we can delete the node in this case, and we can make its parent left field or right field wherever the node to be deleted exists as null. So this is the first condition. Then second condition is that the node to be deleted has only child, that is only one subtree or one child we can say, then its only son can be moved up to take its place. So whether it is left child existing, it will be shifted to take place the place of the parent or the node to be deleted. If there is no left subtree, then the right child will take place the node to be deleted. This is the second condition. We will see the example, then it will be more clear. And the third condition is that the node say P which is to be deleted has 2 subtree, that is it has left subtree as well as right subtree. So in this case, who will replace this node or the node P to be deleted? So there are 2 choices in fact. Either its in-order successor, say S, must take its place, or it will be the in-order predecessor which will take its place. So if we see the in-order successor, so it will be the smallest node into the right subtree. But if we replace the node to be deleted by its in-order predecessor, then it will be the biggest or largest node into the left subtree. So in that case, so this in-order successor or in-order predecessor, first that will be deleted. To delete that node, we have to, so either of the previous 2 conditions can be used. If it satisfies the first condition, then it will use this way. Otherwise it will satisfy second condition, that it will be deleted first by using that, then the actual node to be deleted is to be done. Here is the example we can see. Say here let me want to delete 30. So we can see that 30 is the leaf node or right child of 25. So simply we can delete it. There is no left child, no right child, so we can simply delete it. And we will get this BST will be this one. But if we want to delete say 5, so 5 is here in the left subtree of the root. So but 5 have one left node, that is 2. So 2 will replace this 5. But if it would not have the left subtree but left node, but it would have right node, then say 4 would have been there, then that would have replaced. That is the, then let the node to be deleted has 2 children. So let 20 is to be deleted. So this 20 can be replaced by either by in-order successor, that is by either by 12, or its in-order successor, that is 12. So 20 can be replaced either by 12 or by 24. So we will get this binary search tree after deletion. So this is about the deletion of binary search tree, and we can see few of the applications of BST. BST are basically used for indexing in database, It can be used to implement searching algorithm. Binary search algorithm is based on that. BST are used to implement Huffman coding algorithm. And as I told that insertion and deletion is faster when it is well. So that is all about today's session. Thank you very much.